Okay, so next we're going to discuss ring opening of epoxides and how we can get different types of products this way. The easiest of these two, in my opinion at least, is using nucleophiles. And nucleophiles can be bases, sort of like we've already seen, but then that should be followed with acid. They can be bases or they can just be good nucleophiles. And so here's what can happen when you have a nucleophile that is entering. What we're going to do is we're going to use that with the epoxide, and it is going to come in to the opposite side of where that OH is. So we can use that to our advantage. With this nucleophile coming in, the nucleophile is going to go to the least substituted. So, sorry, let me write that in. So least substituted is where that nucleophile is going to go. Reason being is that you end up with a negatively charged oxygen. So another way that I like to look at that is that the oxygen will go where it is going to be most stabilized, because it's not always necessarily just the least substituted, it's the one where the oxygen's most stabilized, because that can be affected by resonance and things like that, right? And then your second step is just to add some form of acid. Oxygen will pick up that hydrogen, and that's where you end up with your ring opening with your nucleophile there. Now I'm giving you stereospecific epoxides where the most substituted, that's defined. If that is not defined, you can end up with two enantiomers. So in other words, if you have a prochiral type of situation, you can end up getting an enantiomer in theory at least. So we can do this with a lot of different products, right? We can get a lot of different reactants with this. So let's go through these really quickly. Remember, you can use OH minus, and that will give you epoxides like that. That would be opposite from one another. If you use OR minus, you end up making the OR right there. CN minus, which usually comes in the form of NaCN, will be right there. RS minus, we can get an SR, so that would be either a thiol or an organic sulfide. We can use a Grignard reagent, and this is really nice because it's going to attack at that same position, and instead of having an elongation of a carbon where you've got an oxygen, it's actually two over from that. So that's where you can get that from. Or if you want to just use lithium aluminum hydride and just get rid of the epoxide so that you get an alcohol, you can use that as well. All those are followed up by H3O plus, and all of those are going to protonate that alcohol. So now we move on to the more complicated of the types of ring openings, and those are acid catalyzed. They're more complicated because in some way we're just trying to understand that the world works as it does, and we try to understand why as scientists. So keep that in mind as we're approaching things here, okay? So acid catalyzed ring opening of epoxides, if you just have acid, we can open that and get a diol. Now, if you use instead alcohol as a solvent, you can end up getting an ether and an alcohol. Or we can use something like HX, and you'll end up getting whatever X that you're using right there. So here's the mechanism. Here's how this works. So first, the oxygen comes in and grabs that hydrogen. And then if you were to have alcohol, or water would do this as well, those electrons come in here and that kicks that out. The alcohol would then come in and grab that hydrogen, and you would get your epoxide here, alcohol there. Keep in mind that this is just a catalytic amount of acid, because how do I know that? Well, I'm reforming my acid when this OH group comes and grabs that hydrogen. Okay, so that's one option. The other option is like if you use HCl. Well, same first step here. So the thing that's partially negative is going to come pick off the thing that's partially positive. Electrons go back to chlorine. Then chlorine becomes a good nucleophile and the OH becomes a good leaving group. This comes in, that moves out, and you end up with Cl on one side versus the other. Now we still have anti-stereochemistry when that is applicable, so those two R groups are going to be opposite from one another. So if one's going in the back, the other one may be going in the front and vice versa. So I'm sort of showing you that by having these at opposite directions from one another. Here's where things get a little bit more complicated though. When it comes to selectivity, when you have this epoxide here, we've got a difference between this carbon having a primary position versus a secondary position, where in other words, we've got one R group on this side of the epoxide, we've got two R groups on this side of the epoxide. Well, if we add HBr in this case, the thing that is attacking is going to go to the least substituted carbon. However, in this case, we have a carbon with one R group versus this one has 1, 2, 3 different carbons. And we add HBr, we get the opposite. So the OH goes to the least substituted and the bromine goes to the most. Why is this the case? Well, the best thing that we can understand about this is that there's a competing steric versus electronic effect that is happening here. Do you stabilize the electronic charges, or do you end up running out of room first? It seems to make the difference. We as scientists are trying to observe and trying to understand that, and so sometimes it's just the way it is. Things aren't as predictable as other stuff. If you have like a position where you've got an epoxide such as this, where we've got a secondary here and a tertiary here, the tertiary is the one that will house the nucleophile. So like HCl in this position will give you an OH there and a Cl here. And so, yeah, this can be a little bit more complicated. Just have to think your way through it, okay? You can do this. See you on the next one.